In algebra, the partial fraction decomposition or partial fraction expansion of a rational function is the operation that consists in expressing the fraction as a sum of a polynomial and one or several fractions with a simpler denominator. The importance of the partial fraction decomposition lies in the fact that it provides an algorithm for computing the antiderivative of a rational function. In symbols, one can use partial fraction expansion to change a rational fraction in the form where f and g are polynomials into an expression of the form where g, j are polynomials that are factors of g, and are in general of lower degree. Thus, the partial fraction decomposition may be seen as the inverse procedure of the more elementary operation of addition of rational fractions, which produces a single rational fraction with a numerator and denominator usually of high degree. The full decomposition pushes the reduction as far as it can go. In other words, the factorization of g is used as much as possible. Thus, the outcome of a full partial fraction expansion expresses that fraction as a sum of a polynomial and one of several fractions, such that the denominator of each fraction is a power of an irreducible polynomial and the numerator is a polynomial of smaller degree than this irreducible polynomial. As factorization of polynomials may be difficult, a coarser decomposition is often preferred, which consists of replacing factorization by square-free factorization. This amounts to replace irreducible by square-free in the preceding description of the outcome. Basic principles. Assume a rational function in one indeterminate x has a denominator that factors is over a field K. Assume further that P and Q have no common factor. By Beer's outside entity for polynomials, there exist polynomials C and D such that thus and hence R may be written as where all numerators are polynomials. Using this idea inductively, we can write R as a sum with denominators powers of irreducible polynomials. To take this further, if required, write as a sum with denominators powers of f and numerators of degree less than f, plus a possible extra polynomial. This can be done by the Euclidean algorithm, polynomial case. The result is the following theorem. Let f and g be non-zero polynomials over a field K. Write G as a product of powers of distinct irreducible polynomials. There are polynomials b and aij with deg aij less than deg pi such that if deg f less than deg g, then be equals 0. Therefore, when the field K is the complex numbers, we can assume that each pi has degree 1. The numerators will be constant. When K is the real numbers, sum of the pi might be quadratic. So, in the partial fraction decomposition, a quotient of a linear polynomial by a power of a quadratic might occur. In the preceding theorem, one may replace distinct irreducible polynomials by pairwise coprime polynomials that are coprime with their derivative. For example, the pi may be the factors of the square-free factorization of g. When K is the field of the rational numbers, as it is typically the case in computer algebra, this allows to replace factorization by greatest common divisor to compute the partial fraction decomposition. Application to symbolic integration. For the purpose of symbolic integration, the preceding result may be refined into theorem. Let f and g be non-zero polynomials over a field K. Write G as a product of powers of pairwise coprime polynomials which have no multiple root in an algebraically closed field. There are polynomials b and cij with deg cij less than deg pi such that where denotes the derivative of this reduces the computation of the antiderivative of a rational function to the integration of the last sum, which is called the logarithmic part, because its antiderivative is a linear combination of logarithms. In fact, there are various methods to compute above decomposition. The one that is the simplest to describe is probably the so-called Hermite's method, as the degree of Cij is bounded by the degree of pi, and the degree of b is the difference of the degrees of f and g. One may write these unknowns polynomials as polynomials with unknown coefficients. reducing the two members of above formula to the same denominator and writing that the coefficients of each power of x are the same in the two numerators. One gets a system of linear equations which can be solved to obtain the desired values for the unknown's coefficients. Procedure. Given two polynomials and where the alpha are distinct constants and p less than n, partial fractions are generally obtained by supposing that and solving for the ci constants by substitution, by equating the coefficients of terms involving the powers of x, or otherwise. A more direct computation, which is strongly related with Lagrange interpolation, consists in writing where is the derivative of the polynomial. This approach does not account for several other cases, but can be modified accordingly. If p q, then it is necessary to perform the Euclidean division of p by q, using polynomial long division, giving p equals eq plus r with r less than n. Dividing by q, this gives, and then seek partial fractions for the remainder fraction. If q contains factors which are irreducible over the given field, then the numerator n of each partial fraction with such a factor f in the denominator must be sought as a polynomial with dag n less than dag f, rather than as a constant. For example, take the following decomposition over R. Suppose q equals rs and s0. Then q has a 0 alpha of multiplicity r, and in the partial fraction decomposition, r of the partial fractions will involve the powers of. For illustration, take s equals 1 to get the following decomposition. Illustration. In an example application of this procedure, 2 can be decomposed in the form clearing denominators shows that 3x plus 5 equals a plus b. Expanding and equating the coefficients of powers of x gives 5 equals a plus b and 3x equals minus 2bx. Solving for a and b yields a equals 13 halves and b equals minus 3 halves. Hence, residue method over the complex numbers. Suppose f is a rational proper fraction, and can be decomposed into let, then according to the uniqueness of Laurent series, aij is the coefficient of the term minus 1 in the Laurent expansion of gij about the point xi, i.e., its residue. This is given directly by the formula, or in the special case when xi is a simple root. When note that p and q may or may not be polynomials. Over the rails, partial fractions are used in real variable integral calculus to find real-valued antiderivatives of rational functions. Partial fraction decomposition of real rational functions is also used to find their inverse Laplace transforms. For applications of partial fraction decomposition over the rails, see application to symbolic integration, above. Partial fractions in Laplace transforms. General result: let f be any rational function over the real numbers. In other words, suppose there exist real polynomials functions p and q0, such that by dividing both the numerator and the denominator by the leading coefficient of q, we may assume without loss of generality that q is monic. By the fundamental theorem of algebra, we can write where a1, and b1, bn, c1, cn are real numbers with by 2 minus 4 ci less than 0, and j1, jm, k1, not so positive integers. The terms are the linear factors of q which correspond to real roots of q, and the terms are the irreducible quadratic factors of q which correspond to pairs of complex conjugate roots of q. Then the partial fraction decomposition of f is the following. Here, p is a polynomial, and the b, and circle are real constants. There are a number of ways the constants can be found. The most straightforward method is to multiply through by the common denominator q. We then obtain an equation of polynomials whose left-hand side is simply p and whose right-hand side has coefficients which are linear expressions of the constants b, and circle. Since two polynomials are equal if and only if their corresponding coefficients are equal, we can equate the coefficients of like terms. In this way, a system of linear equations is obtained which always has a unique solution. This solution can be found using any of the standard methods of linear algebra. It can also be found with limits. Examples. Example 1 here, the denominator splits into two distinct linear factors. So we have a partial fraction decomposition multiplying through by x2 plus 2x minus 3. We have the polynomial identity substituting x equals minus 3 into this equation gives a equals minus 1/4, and substituting x equals 1 gives b equals 1/4. So that example 2 after long division, we have since 2 minus 4 times 8 equals minus 16 less than 0, the factor x2 minus 4x plus 8 is irreducible, and the partial fraction decomposition over the rails has the shape multiplying through by x3 minus 4 by 2 plus 8x. We have the polynomial identity taking x equals 0, we see that 16 equals 8a, so a equals 2. Comparing the x2 coefficients, we see that 4 equals a plus b equals 2 plus b, so b equals 2. Comparing linear coefficients, we see that minus 8 equals minus 4a plus c equals minus 8 plus c, so c equals 0. Altogether, example 3. This example illustrates almost all the tricks we might need to use, short of consulting a computer algebra system. After long division and factoring the denominator, we have the partial fraction decomposition takes the form multiplying through by 32. We have the polynomial identity taking x equals 1 gives 4 equals 4c, so c equals 1. Similarly, taking x equals I gives 2 plus 2i equals, so phi plus g equals 1, so f equals 0 and g equals 1 by equating real and imaginary parts. With c equals g equals 1 and f equals 0, taking x equals 0 we get a minus b plus 1 minus e minus 1 equals 0, thus e equals a minus b. We now have the identity expanding and sorting by exponents of x we can now compare the coefficients and see that with a equals 2 minus d and minus a minus 3d equals minus 4 we get a equals d equals 1 and so b equals 0. Furthermore, as c equals 1, e equals a minus b equals 1, f equals 0 and g equals 1. The partial fraction decomposition of f is thus alternatively, instead of expanding, one can obtain other linear dependencies on the coefficients computing some derivatives at x equals 1 and at x equals I in the above polynomial identity. MP vanishes if m greater than 1 and it is just p if m equals 1. Thus, for instance, the first derivative at x equals 1 gives that is 8 equals 4b plus 8 so b equals 0. Example 4. Thus, f can be decomposed into rational functions whose denominators are z plus 1, z minus 1, z plus I, z minus I. Since each term is of power 1, minus 1, 1, minus I and I are simple poles. Hence, the residues associated with each pole, given by r, respectively, and example 5 limits can be used to find a partial fraction decomposition. First, factor the denominator. The decomposition takes the form of as the a term dominates, so the right-hand side approaches. Thus, we have as the right-hand side is thus at. Therefore, the decomposition is thus the role of the Taylor polynomial. The partial fraction decomposition of a rational function can be related to Taylor's theorem as follows. Let be real or complex polynomials. Assume that in that define also then we have if, and only if, for each the polynomial is the Taylor polynomial of order at the point. Taylor's theorem then provides a proof of the existence and uniqueness of the partial fraction decomposition, and a characterization of the coefficients. Sketch of the proof. The above partial fraction decomposition implies, for each one IR, a polynomial expansion, as so is the Taylor polynomial of, because of the unicity of the polynomial expansion of order, and by assumption Conversely, if the are the Taylor polynomials, the above expansions at each hold, therefore we also have as, which implies that the polynomial is divisible by for also is divisible by, so we have in turn that is divisible by. Since we then have, and we find, the partial fraction decomposition dividing by fractions of integers. The idea of partial fractions can be generalized to other integral domains. Say the ring of integers where prime numbers take the role of irreducible denominators. For example,